Last class, we started talking about radioactivity because that's what people wanted to talk about next. So we're going to pick up where we left off last class. We had reviewed our nuclear symbols. So we've got a couple of different ways that we can represent a particular nuclide. And we looked at those. And we've got the main subatomic particles, the particles that make up an atom, our proton, our neutron, our electron, and symbols that we use for those. Those are going to become important because when we're talking about radioactivity and nuclear decay, we are talking a lot of the time about subatomic particles. So our first type of decay is alpha decay. In alpha decay, an unstable nucleus, so the core of an atom, releases an alpha particle. An alpha particle is the same as a helium nucleus. And so our alpha particle has this symbol, 4/2 He. Since a helium nucleus contains 2 protons, that's what the 2 is for, and 2 neutrons. And 2 plus 2, as we know, 4. So that's why it's 4/2. 4 total count of protons and neutrons, and a 2 for 2 protons. The symbol is He, because we'll never be him. Oh, sorry, because it's helium, and that's our symbol for helium. And that's our alpha decay. The way that we write out a lot of our nuclear decay or nuclear emission processes is with a nuclear equation. In our nuclear equation, the sum of protons, or I guess the sum of mass number, and atomic number must be the same on both sides. Which is kind of what these italicized bullet points say. So for example, in this nuclear decay equation, we're undergoing alpha decay. So our parent nuclide, the one that we started with, is uranium-238. So starting with uranium-238, our mass number is 238. If we look at the product side of the reaction, the parent nuclide produces a daughter nuclide and also an alpha particle. And our daughter nuclide has a mass number of 234. 234 plus 4 equals 238. Our mass number is conserved. And our atomic number is 92 for uranium. Thorium, it's thorium because it's 90, and we subtracted 2. We lost 2 in our alpha particle. So often what I'll do when I'm solving these, and what you might want to do as well, is we'll just make little equations like this. So for example, if we're looking at the mass number, we might not know. We probably won't know that it's 234 for our daughter nuclide, for our thorium in this case, our TH. We wouldn't know that it's 234, but we know that we're losing an alpha particle, and our alpha particle has a mass number of 4. So we could write 238 equals x plus 4. And then we just solve for x. It's like the simplest algebra problem that we could possibly have. You might not even need a calculator for a lot of this, which is great. And we would do the same process for the bottom side. For example, we wouldn't know that it's 90, but we memorized that our alpha particle is 4/2 He. And so we know that we've got a 2 for our atomic number, and so we could write 92 equals y plus 2. If we solve for x and y, That gives us our mass number and our atomic number. Our atomic number is linked to our symbol, so we can get the symbol then from the periodic table. So it's just an example of what this process might look like. But it requires us to have memorized our alpha particle and to know which side that goes on in our decay equation. In a lot of nuclear reactions, the elements are going to change their identities. So they will move from being one element to being a different element. Not all of them, but many of them. And this is what I was talking about. We can come up with, we can make little nuclear equations. So for example, starting with the thorium-232, we know that we're undergoing alpha decay. And so we can make this equation, 232 equals x plus 4. We solve for x, it's 228. So then in place of that, x over y question mark, it would be 228. We also solve for the bottom, 90 equals y plus 2, since the atomic number has to be the same on the right side as on the left side. So we come to the conclusion, well, that must be 88. And then we would look at our periodic table and find 88. That's going to be Ra. So we would write the symbol Ra here, and that would be our daughter nuclide. That's what we would call it. So the math part, I think this is some of the easier math that we do in the class. It's just that you have to learn how to set up the problem correctly. Do we have any questions? Yes? We could also use it to find the parent nuclide. So if we have the daughter nuclide, if we've got the two things on the right side, if we've got the daughter nuclide and we know what type of decay it went through, we could work backwards and solve for the parent nuclide as well, yes. All right, an example. Write the nuclear equation for the alpha decay of uranium-238. And this is what a problem might look like on an exam, or it might just ask you what this decays to. So the two important pieces of information that we're given here, it's alpha decay and it's uranium-238. So alpha decay should trigger in our minds alpha particle, 4 over 2 He. And this U-238, the 238 is that top number, it's the A, the atomic weight, the mass number. Then we write U after that, that's our symbol. And we would look at a periodic table to figure out what our atomic number is, that's the lower number. It's 92. And then we have to set up our nuclear equation. So uranium-238 is decaying. So it goes on the left side, and then we write our arrow. And we're going to make something our daughter nuclide. And there's also going to be the alpha particle that's emitted. Then we can set up our two equations. 238 equals x plus 4, and 92 equals y plus 2. You don't have to call it x and y. You can call it whatever you want. I just use x and y because those are some familiar algebra variables. You could call them a and z. And then we do a little bit of math. So solving for x, x is 238 minus 4, so it's 234. Solving for y, subtract 2 from both sides, and y is 92 minus 2, so it's 90. And then these numbers come back and fill in for our daughter nuclide. So 234 over 90. Then we go to our periodic table. We find 90. 90 is TH. So we put a TH for our symbol. And that's a complete nuclear equation. Question? Yeah, so 232.04 is the average mass of thorium. So in the wild, if you just collected a bunch of thorium and you figured out the percentage breakdown of all the different masses of thorium, the different isotopes, on average it's around 232. But there are some isotopes that are heavier, so this is one of those heavier isotopes. This is 2 extra neutrons compared to the average thorium that you would find in the wild. All right, so thinking about some of the properties of alpha decay, we're going to use a traffic analogy here. So alpha radiation, this is a semi-truck, our 18-wheeler of radioactivity. If you're out on the road, typically an 18-wheeler is the biggest thing that you're going to see out there. This is our most massive particle. It's the biggest in size. It's 2 protons and 2 neutrons. It has the highest ionizing power, meaning that it causes the most damage when it crashes, just like an 18-wheeler truck. So when particles hit each other, if you get hit by a really high energy particle, that can cause whatever it hit to break. So like if it hits a strand of DNA, it might break off part of your strand of DNA, or it might, cut it in half, or it might break a cell that's in your body or something. It might ruin the membrane. And the bigger that the particle is, the more energy that it's going to carry with the same amount of speed. So these ones are going to cause a lot of damage when they crash into your body. They're more likely to disrupt your cells. But they also have the lowest penetrating power, so they get stopped pretty easily. With our 18-wheeler analogy, you have hopefully never in your life seen an 18-wheeler truck skipping traffic by driving on the edges. I can't remember what the edges of the highway are called, but you probably have never seen just running off along the side. You've probably seen some sedans do that, and you've definitely seen some motorcycles cruising between lanes, right? You're never going to see that, hopefully, with an 18-wheeler truck. That sounds terrifying. So it's very big, alpha radiation, alpha particles, big heavy particles, lots of ionizing power. They're going to cause a lot of damage, but low penetrating power. They're going to crash into the first thing that they come to. They're not going to be able to weave through traffic. So for the most part, radiation, this penetrating power that we were talking about, radiation needs to get into a cell, or it needs to get into important cells for it to cause actual amounts of damage to our bodies. Fortunately for us, we've got a couple layers of skin, right? It's like 7 layers of skin or something. I don't remember biology that well. But our skin is relatively tough compared to our insides. Our inner bits are, soft and squishy. Our skin relatively not soft and squishy. So if we get hit by alpha radiation on the outside, it's not that big of a deal. Our skin is used to, handling UV radiation. It's not going to screw us up too bad. Our skin gets replaced all the time anyway. But if you get it inside of you, that high ionizing power or that low penetrating power doesn't really matter because it's next to all the soft squishy bits that are important. And so it's going to cause damage if you ingest alpha radiation. Otherwise, it can be stuck by a sheet of paper, clothing, or even just air. So if you're just far enough away from the alpha radiation source, it'll just run into air particles, gas particles that are between you and the alpha source. And so you're not in that much danger, generally, with alpha sources. So that's our first type of decay. Our second type of decay is beta decay. In beta decay, an unstable nucleus emits an electron. So our beta particle is the same as an electron. So the net result of beta decay is that a neutron turns into a proton and there's an emitted electron. And if this doesn't make sense to you, you can revert back to just make the mass numbers equal, make the atomic numbers equal on both sides. The math works out for this. So on the left side, we've got 1 for our mass number. We have 1 for our mass number for a proton and 0 for our electron, our beta particle. Our neutron has an atomic number of 0 since it's not a proton. Our proton has a number of 1. Our electron has a number -1. So the 1 and the -1 cancel out to equal that 0. Write in little pluses and equals there. So in this example with Ra, it moves up to AC on the periodic table. So it shifts 1 spot to the right, one spot up, I'll put right, 1 spot right on the periodic table. And it has the same mass number. If you remember way back to one of the first-ish weeks of this class, we talked about the differences in the size of protons and neutrons. Those are about the same versus an electron. An electron is about 2,000 times smaller than a proton or a neutron. So the comparison that I made at that time was if the electron's like a watermelon, then a proton or a neutron is like a semi-truck. So this electron is much, much smaller than our alpha particle, which is 2 protons and 2 neutrons, like 8,000 times difference in size. Carbon-14 is a radioactive isotope of carbon. Let's write a nuclear equation for the beta decay. So the 2 important parts, it's beta decay, and we're starting with carbon-14. Beta decay means we're working with our beta particle, 0 over -1 e. It's an electron. I think of this -1 as its charge. And then carbon-14, our symbol is C. The 14 is our mass number. And we can find our atomic number from the periodic table. It's 6. So we're going to set up with 14 over 6C. On the left side, that's our parent nuclide. It's undergoing decay. It's going to make the daughter nuclide and also our electron. So our top equation for our mass numbers, 14 equals x plus 0. Pretty easy math. So x is 14. And then for y, 6 equals y plus -1, or just -1. So we add 1 to both sides to get rid of that -1. Y equals 6 plus 1. Again, easy math, hopefully. So y is now 7. So 14 over 7, and then we go to our periodic table to see what has the atomic number 7, and it's nitrogen, N. So 14 over 7, N. And that's our whole nuclear equation for the beta decay of carbon-14. Question?
The nitrogen would be the daughter nuclide?
Yes, the nitrogen is the daughter nuclide. All right, so thinking about beta decay in the world of our traffic analogy, this is our 4-door or 2-door, just any size of sedan of radioactivity. They are, beta particles that is, are much less massive than alpha particles. They're about 8,000 times less massive. So a watermelon compared to 4 semi-trucks. They have lower ionizing power, but higher penetrating power compared to our alpha particles. So the lower ionizing power, if we think of car crashes, a semi-truck crashing is going to cause a lot of damage, obviously, hopefully. If you have a sedan, just a regular car that crashes at the same speed, that's going to cause a lot less damage to whatever it crashed into. If you had to choose between the two of them, which would you rather get hit by, a semi-truck or a regular sedan?
Sedan.
Hopefully a sedan. If you chose a semi-truck, we have mental health services available on campus that are, I think, free. So lower ionizing power is going to cause less damage when it crashes into something, but it also has higher penetrating power. It will maneuver through traffic more easily. Occasionally you'll see them driving up the side of the highway because they have somewhere that's apparently really important for them to be. Or they just can't be bothered to sit in traffic. So these can be stopped by a sheet of metal or a thick piece of wood, versus the alpha particles were stopped by possibly just air or clothing or like a sheet of paper. So a sheet of metal, thick piece of wood, that's a lot more to get through. And that means that they're more dangerous when they're outside of the body. They have better ability to penetrate into your body and cause damage to your insides even from the outside. But if you ingest them, if you get them inside of you, where they're right next to all the squishy, soft, important bits, they do less damage because they have less ionizing power. So they're not going to mess you up as much if you get them inside of you. And then gamma radiation is our third type of radiation. And gamma ray emission is a form of electromagnetic radiation. So it's a type of light, sort of. They're just high energy photons. So think turbocharged UV light or X-rays. It's higher energy than both of those. We're the far end of the high energy spectrum for electromagnetic radiation when we covered that in chapter 9, whenever that was. Gamma rays have no charge and no mass. And so if you just do gamma radiation, nothing changes. It's just releasing energy. So typically these are emitted with other types of radiation. So a sidekick to alpha or beta decay, for example. Not always, but sometimes. And since there's no change, or it's in conjunction with other types of radiation, we don't have an example to do for this one. Gamma rays are the motorcycle or the motorbike of radioactivity. The lowest ionizing power. Again, if we had to choose between being hit by vehicles that can go on the highway, and our options are motorcycle, sedan, semi-truck, and they're all traveling at the same speed, Hopefully we're picking motorcycle, right? That's the one that's going to probably mess you up the least. But they also have the highest penetrating power. You will frequently see people on motorcycles, if there's traffic, just riding between the cars. They can get through traffic pretty much no problem. Traffic doesn't apply to them. And that kind of follows along with the penetrating power of gamma rays. They can be stopped by several inches of lead shielding. So oftentimes if you're working with them in the lab, you'll have lead bricks that you can arrange to form a barrier, or you'll have lead-infused glass. Or if you've got really large amounts or a large area to protect, you might use thick slabs of concrete, like multiple inches thick concrete. And that will stop gamma radiation, gamma rays. And then our last type that we'll learn for this class is positron emission. The positron is the antiparticle of the electron. So it's the opposite charge. That's all that you need to know really for this class. Is it's just an opposite charge electron. It's positively charged instead of negatively charged because if somehow you got a positron to collide with an electron, since they're antiparticles, they would just get destroyed and then release a bunch of gamma rays. So if for some reason you have a positron and an electron, keep them away from each other or they'll blow up. In positron emission, it's the opposite of our beta decay. In our beta decay, we were taking a neutron and turning it into a proton. And our beta particle, our electron, this is the opposite direction. So we're taking a proton, turning it into a neutron. When an atom emits a positron, its atomic number just drops by 1 on the periodic table. And these have the same size and energy as beta particles, electrons. They're like shadow fighters. I think that's what they're called, right? Like if you're playing Smash Bros, right? Pit and Dark Pit. It's a shiny version of an electron, like Pokemon. So this is our fourth type of radiation, but you don't really have to memorize anything. Like the gamma one is just 0, 0, so there's not really anything to memorize for that one. So like sort of, we just have 3 different types of particles to memorize. And it's really only 2 because it's the positron and the electron. They're just opposite charges. So it's sort of 2 particles and a half. All right, so let's do an example for positron emission of sodium-22. We would need to remember what our positron is. It's 0 plus 1 positive positron. And the symbol is E. Electrons used to be called negatrons. I don't know why we stopped calling them negatrons, but negatron would be negative, positron would be positive. That works out pretty nicely here. And this is for sodium-22. So the 22 referring to the mass number. We would find the atomic number on the periodic table, it's 11. So 22 over 11 Na. So then our nuclear equation, we're starting with 22 over 11 Na, going to a daughter nuclide and 0 over plus 1 E, our positron. Set up our equations. 22 equals x plus 0, so x is 22. And then for our atomic number, 11 equals y plus 1. So y equals 11 minus 1, which is 10. So 22 over 10, and 10 is neon. So this is neon 22. And then for a summary, here's this table modified from our book for the 4 types of particles that you need to know about for this class. The symbols are a little bit different, like in these generics, alpha, beta, etc. In nature, these radioactive materials just naturally occur. They're all over the place. And the natural radioactive elements either have a very long half-life, because everything was kind of generated one time. They either have a very long half-life, or they're continually formed by some other process. That's just like they're here, so they must be being formed, or they just have been around for a long time. Uranium is our heaviest naturally occurring element. It decays to thorium-234 with a half-life of 4.47 billion years. So that's a long time. Thorium-234, though, is radioactive and decays to protactinium Pa-234 with a half-life of 24.1 days. So that's not around for very long. You can still find thorium-234 out in the wild, though, because this uranium that takes forever and a half to decay is constantly producing it. So there's little amounts out there, and you can collect them. But you have to work quick. It's half-life of 24.1 days. So it goes away pretty rapidly. So this uranium-234 as an example of the long half-life, and thorium-234 an example of something that's continually formed. You don't need to know those as specific examples, just why those are here. Oftentimes, when you've got one radioactive decay event, you'll also have other radioactive decay events, and it can get a little bit messy. So that protactinium-234 that we talked about in the previous slide, can decay back to uranium with a half-life of 244,500 years. And then that can go through a series of alpha decays. And then we've got a bunch of choices of alpha and beta decays. And it's this whole messy web of things that can be made. You don't need to know this, like any of the specific details of this. Just the main idea being that usually there's a chain of events until we end up at something that's stable. And that thing that's stable is lead. Lead is typically the endpoint for a lot of these radioactive decay processes. So all of the uranium-238 that's out in the wilderness, out in the wild with that super long half-life, if we skip forward, maybe 100 billion years, it'll all have turned into lead-206. And we'll all be long gone, so we don't have to worry about that. Plenty of U-238 for our lifetime. Radioactivity is a natural component of the environment. You are exposed to radioactivity, like nuclear radioactivity, just kind of on a regular basis, but it's a really small amount. There's a little bit that makes it through from space, and there's some in things that are in the ground. There might also, if you're like drinking on well water, there is a little bit of uranium in the well water around here, so you might be consuming a small amount of uranium. Not enough to give you superpowers. Any questions before we start on Half-Life, not the video game? All right, so radioactive nuclides decay at different rates. That's the half-lives that we were talking about. Half-life is a concept that is confusing for some people. It's reasonable that it's confusing. It's not the most straightforward concept. But half-life is the time it takes for half of the nuclides to decay. So after one half-life, 50% of the sample is gone. After one half-life, 50% is gone. Whatever we started with, 50% of it has decayed after one half-life. If we go forward another half-life, this is the part that often confuses people. They think, okay, well, we've gone through two half-lives. If it's 50% each time, now it's all gone. That is not how it works. It's 50% of the amount that we had at the start of that half-life. So we went through one half-life, we went down to 50%. We go through another half-life, we cut the 50% in half. Now we're down to 25%. So it decays 50% each half-life from the previous amount. So it's like stepwise cutting it in half instead of adding up. And that's the part that often gets people. Do we have any questions about that? So after one half-life, it's cut in half. Two half-lives would be fourths. Three half-lives would be an eighth. Four half-lives, 16ths. Five half-lives, 32nd. You can have many, many half-lives that occur, and you still have some left. It's kind of the takeaway. It's not all gone after two half-lives. Nuclides that decay quickly have short half-lives and are considered very active. They have a lot of decay events per minute or per unit time. So lots of alpha particles or beta particles or gamma rays being emitted. For example, radon-220 has a half-life of approximately 1 minute. So if you have, let's say, 1 million radon-220 atoms, and you wait a minute, then you're down to 500,000. If you wait one more minute, half of those 500,000 are gone, and you're down to 250,000. And then you'd be down to an eighth, and then and so on and so forth. And radium-220 is not something that you would want to be around because it's very active. It's going to be releasing a lot of particles or a lot of rays. So the same amount versus a slower, a much less active nuclide like thorium-232, that radon-220 is going to do a lot more damage to you because it's emitting a lot more radiation. Thorium-232 is much less active. It's got a half-life of 14 billion years. So you're going to get fewer particles emitted, fewer decay events per unit time. So more active means more decay events, less active, fewer decay events. And this is what half-life looks like on a graph. So our graph here, we're graphing on the y-axis the percentage of radioactive material remaining. We start with 100%. Whatever the amount is, it could be grams, it could be atoms, it could be moles, but whatever we started with, it's 100%. And then we've got our half-lives measured here on the x-axis. So at one half-life, we're down to half the amount, 50%. We cut that in half again after two half-lives, so we're down to 25%. We cut that in half again at 3, so we're down to 12.5%. And for 4, we cut it in half again, so we're down to like 6%, 6.25%, something like that. Just sequentially cutting it in half. Each radioactive nuclide has a unique half-life. It is not affected by physical conditions or chemical environment. So if you heat up the nuclide a lot, if you heat it up to 10,000 degrees Celsius, or if you cool it down to 1 degree Celsius, doesn't matter. If you put it around lots of loud noise or in a really quiet environment, none of that's going to change anything. It's always going to have the same nuclear decay half-life. And you'll always be given half-lives if you need them on a test question. So let's do a practice problem with half-life. We've got plutonium-43 sample. And initially it contains 0.256 moles. We want to know how much plutonium is left after 30 hours. And we're told the half-life is 5 hours. So one of the important pieces of information we need to know here is that after one half-life, half of the sample goes away. So one half-life cuts the amount in half. Basically, we divide by 2. So if we've gone through 30 hours, how many half-lives have we gone through? 6 half-lives. So 30 hours, 5 hours per one half-life. The symbol for half-life is T1/2 usually. I'm just tired of writing half-life is all that it is. So I'm telling you that's what we're using instead. So we do 30 divided by the time for our half-life and we get a number of 6. Six half-lives. If each half-life cuts it in half, then we're going to cut it in half 6 times. So cut the initial amount in half 6 times. So what that means is we're going to take 0.256 moles and we're going to divide by 2 6 times. You can either do that sequentially or all at once. So you could take 0.256, divide by 2, press equals, or press enter on your calculator, and then do it 5 more times. Or you can do it all at once. The fastest way to do this on your calculator would be 0.256 over 2 raised to the 6th power. That's the fewest button presses. The 2 because we're cutting it in half. And the 6 because of 6 half-lives. So 0.256 divided by 2, divided by 2, 3, 4, 5, 6, 0.004. The only thing that I would worry about, like if we're doing it 6 times, is that I just miscounted, right? So we can also do 2 raised to the 6th power. And I counted correctly, thank goodness. It is 0.004. So 0.004 moles remains after 30 hours. Questions? It's the half-life stuff about radioactivity, I think, that tends to confuse people the most. So if you're confused, please come to office hours, ask me in lab, ask questions during lecture. If you're not confused, great, awesome. There are a couple of ways that we can detect radioactivity. The one that you're probably familiar with is a Geiger counter or a Geiger-Müller counter. And this is like a little box that you would hold in your hand. They're like, the box thing is like, I think this big-ish for the top. They're about yay tall. A little black handle, and then it's got like a magic wand thing that you pull off, and it looks like you're interviewing somebody. And this, on the diagram, this is the part that you would hold in your hand. And then this is the part that would be embedded into that box. And so you just point the wand at something, and it tells you if there's radioactivity there or not. There's usually like a sensitivity knob, and then you can have it make noises or not make noises. So if you've played the Fallout games, the clicking sound that you hear when you're in radiation, that's the sound of the Geiger-Müller counter. Basically the same idea. And these are really nice because they're portable. So you can carry one around with you. So if you're working with radioactivity and you're not sure where you're going to need to check it, it's handheld, it's portable, so you can just wave it around at stuff, point it at things. They're very portable. And that's, I think, the most important way to detect radioactivity. There's more details in the slides if you want to read it, but that's the basic idea. One thing that we can do with our knowledge of half-life and decay processes is radiocarbon dating, or as you've probably heard it, carbon dating. So carbon dating can be used because of natural radioactivity in our environment. You can use it to estimate the ages of fossils and other artifacts, kind of just old stuff that's out in the environment. Lots of ancient artifacts, not all, but lots of them, contain a radioactive signature that reveals their age. And this is based off of the presence of radioactive carbon-14 in the environment. So it's specifically carbon-14, and the carbon is why it's called carbon or radiocarbon dating. So carbon-14 is one of those radioactive materials that's constantly being formed. The process, though, is not from decay of something else. It's constantly being formed in the upper atmosphere by neutron bombardment from space of nitrogen. So nitrogen is a big component of our atmosphere. It's mostly nitrogen. So up in the upper atmosphere where there's less clouds and less of our atmosphere in the way, some of those nitrogen atoms or molecules up there can get bombarded or hit with a neutron and turn it into carbon-14. Hydrogen is also produced in the process. And then this carbon-14 is unstable. So it can decay back to nitrogen by releasing an electron, a beta particle. And we know that this has a half-life of 5,730 years. So it's a relatively slow process for our lifetimes, but it's a lot quicker than like 14 billion years. And the way that we use this knowledge, that we use this information, is that it's continuously being formed and it constantly decays. And because of that, over the millennia that the Earth has been here, there's sort of been an equilibrium established of carbon-14 produced in the upper atmosphere and then it decaying. And that carbon-14 that's up in the upper atmosphere can be oxidized, turned into carbon dioxide, work its way down into our breathing space, get picked up by plants. The plants then have some carbon-14 in them. We eat the plants, or something else eats the plants, and we eat what ate the plants, et cetera, right? There's a whole food chain. The carbon-14, though, one way or another works its way into living organisms. So living organisms, all of them, are consuming some amount of carbon-14. That includes us. And then one of the things that happens when you die is you stop eating. Once you're dead, no more eating. That's it. So get in while you can, just not too much. You might die sooner if you do. All right, so we're going to eat carbon-14 until we die. And then once we die, we're going to stop incorporating new carbon-14. So boom, we've got the maximum amount of carbon-14 that we're going to have for the rest of our disintegration period, our decay period. So as we decay, so does the carbon-14. So once you die, you're not consuming any more carbon-14, and so the amount that you had in you, or the amount that a plant had in it, right, decays over time. And because of its natural decay series, or its natural decay process, its half-life of 5,730 years, we can predict back the amount of time based on the amount of carbon-14. You don't need to be familiar with or savvy with all of the details exactly. The rough estimate for the upper end of carbon dating is somewhere on the order of 50,000 years. Something like 9 half-lives. So once we've cut the amount in half, about 9 times, that's kind of borderline where we can measure accurately. The way that we would check age is against objects whose ages are known from historical sources. It's like if we have really old writing samples and we know about when they were produced, or like counting the tree rings, or maybe ice cores, since ice cores can also be used to estimate age or time. And there's a little bit of a deviation because the atmospheric carbon-14 levels aren't exactly stable, they're just roughly stable. There's a little bit of plus or minus. All right, so let's use some of this knowledge that we've learned. An artifact peddler claims to have a partially fossilized grave marker from a peat bog in modern Denmark. I visited Denmark last year, that's why this is in here. The marker is inscribed with runes consistent with writing from the 700 CE, CE being the same as AD. A measure of its carbon-14 content revealed to contain 100% of that found in living organisms. Is the grave marker authentic? Carbon-14 has a half-life of 5,730 years. So the beginning part here is just flavor text. The important parts are the runes are consistent with the 700s CE, so about 1,300 years ago. And it contains 100% of the amount found in living organisms. And carbon-14 has a half-life of 5,730 years. If it was if the marker was from 700 CE, would we expect it to have the same carbon as living organisms? Should it have the same amount of carbon-14 in it as things that are alive today? No, why not? So the correct answer is no. It shouldn't have 100%. That's a sign that it's not authentic. Why not? Presumably the grave marker, right, made from a dead tree or something like that. When it died, it stopped incorporating new carbon-14 into its self. And that carbon, even though it has a half-life of 5,730 years, 1,300 years is like a quarter of that. That's a significant amount of time. We would expect to see some decay. It should have less than 100% of that found in living organisms. So no, it should have less than 100% of the C14 in living organisms. And the reason, because the carbon-14 should have decayed. A bit. We don't know. We don't have the tools for this class to know exactly how much it would have decayed. But it should have decayed some amount, and it would be a measurable amount. Questions? Okay, we'll take a pause on the math and do some history. This history is largely taken from a book, so it might be, a little bit plus or minus on the accuracy. We'll see. I mean, I won't see, but take it with a grain of salt. In the mid-1930s, Enrico Fermi is a famous physicist, attempted to synthesize a new element. Some chemists are often trying to find new elements, and he thought, let's bombard uranium with neutrons. If you incorporate that neutron into the nucleus, then it might undergo beta decay. That beta decay would tick it up 1 on the periodic table by converting that neutron into a proton. And he detected beta emission, and so he thought, I've done it. I made the new element. I got the beta emission that I was thinking I was going to get, but he didn't actually look at the products to determine if a new element had been formed. The history stuff is mostly just like an FYI, so don't worry about memorizing it. Some other chemists at the time, physicists at the time, I don't know which, Meitner, Strassmann, and Hahn repeated Fermi's experiments, and they found that it wasn't a heavier element, but there were actually several elements that were lighter than uranium. And this was a big discovery for the time. On January 6, 1939, they reported that neutron bombardment of uranium resulted in nuclear fission. So nucleus pertaining to the nucleus, or nuclear pertaining to the nucleus, and fission splitting. So what was actually happening was not that the neutron was being incorporated and it was becoming bigger. That neutron was hitting the nucleus and breaking it into smaller pieces. It split into barium, krypton, and 3 neutrons and released a massive amount of energy. And since we started with a neutron and we produced 3 neutrons, this has the potential to undergo a chain reaction if you have a sufficient amount of uranium-235. So these neutrons can go on to hit other uranium-235 nucleuses and cause this process to happen again. And this is what happens in an atomic bomb. So if you've got enough of this uranium-235, the nuclide that can undergo this chain reaction, then you can get a self-sustaining reaction. Self-sustaining nuclear fission. And eventually it gets to the point that the amount of energy that it releases is what causes an atomic explosion. So if you have enough uranium-235, you can make a nuclear weapon. In 1942, the US launched the Manhattan Project in Los Alamos, New Mexico, and the first nuclear weapon was detonated in 1945 with an equivalent force of 18,000 tons of dynamite. The bomb, of course, being much smaller than that. Germany had already surrendered at that point, but 2 bombs were dropped on Japan, and at least 200,000 people were killed. So that's kind of the dark side of fission. But there's a not as dark side of fission, and you can control a fission reaction to generate electricity. So this is what nuclear power plants use currently. So you can generate electricity with no air pollution or greenhouse gases, so you don't really have to worry about emissions. Currently, fission nuclear is about 20% of US electricity. That's mostly because we're scared of electricity well, we're scared of nuclear in the US compared to like Europe and other countries where it might be as high as 70%. It's also very energy dense. So a pencil-sized cylinder of uranium could power a typical car for 20 years. This is the tech behind nuclear submarines. And a coal burning plant that uses 2 million kilograms of fuel generates the same amount as 50 kilograms of fuel in a nuclear plant. So the energy density is vastly different for the two. There are, of course, some downsides to nuclear, but it is much cleaner on the whole. This is an example of what a nuclear reaction used in a power generator might look like. So the actual nuclear part is this bottom part here. So we've got our reactor core, and the reactor core has fuel rods that are all next to each other, and then it's got control rods that drop in between them and absorb neutrons. So if you drop the control rods inside, these are retractable neutron-absorbing control rods. If you drop the control rods down, that stops the fuel rods from being able to interact with each other and continue the nuclear reaction. If you lift them up, it allows them to ramp up the nuclear reaction. If you pull them up all the way, then that's the sort of thing that you might get to like a nuclear meltdown, for example. One of the big nuclear meltdowns, there were some safety issues. I think for one of them, they had set the default controls to have the nuclear rods all the way up. So there was like a power cycle that happened, and then the control rods all got lifted up, and the reaction went supercritical and then exploded. So that's just a bad engineering on their part there. Otherwise, you just have some very fancy water, from what I've been led to believe on YouTube. There's some fancy water that's in there. It generates steam, and then steam turns turbines that turns into power. So typically, nuclear reactors are on the coast or near some big water source for cooling purposes. There's also nuclear fusion. So fusion is, rather than splitting, it's combining. And fusion is great because you can take 2 light nuclei, 2 small atoms, and merge them together to form a heavier one. And this is what happens in the sun. The sun is turning hydrogen into helium. And this is typically what people talk about when they're talking about nuclear fusion, like fusion reactors. These are also still highly exothermic, and that has to do with the properties of the nuclides. It has to do with the glue that holds them together, their binding energy. This has some advantages. One of them is that it's got 1,000 times more the explosive force. If you like war, then that's great for that. But it also means that there's even more energy that's produced by nuclear fusion versus fission. So there's way more possibility for power output. Combine that with the fact that we're mixing two hydrogen nucleuses and making it into helium. Helium, which we use to run MRI machines and mass spectrometers and lots of other things, fill up party balloons, right? And we're actually running out of helium, so if we can get nuclear fusion down, that's a great way to get helium-4. And it takes a lot of energy, so a small fission bomb or some other large amount of energy needs to be invested to start a nuclear fusion reaction. So hopefully in our lifetime we'll see nuclear fusion take off. It's about 10 times higher energy density than fission, less problematic products. We actually need more helium. The problem with it is that nothing can extend or withstand the extreme temperatures. So this is a picture inside of one of the reactors for fusion. It's achieved a plasma temperature of 20 million degrees Kelvin. So that'll melt anything. And that's part of the problem. You can't just like hold it in. You can't like add water to it. So there's some issues. I think there have been a couple of test experiments where they've gotten the same amount of energy out that they put in for like a couple minutes, and that's kind of where we are with nuclear fusion, so who knows? It's been 10 years away for the last 30 years. Other things that happen with radiation is you can get acute radiation damage. So acute here means just short time scale, not short Tim scale. Short time scale. So radiation damage from exposures to large amounts of radiation in a short amount of time. The big places that you might experience this, a nuclear bomb, or if you were exposed to a nuclear reactor core or other nuclear material for a significant amount of time, and it causes bad things to happen. So large numbers of your cell will die, your immune system, your intestinal lining, the parts that are prone to damage from radiation. So you might have a weakened immune system, not be able to absorb nutrients. If you get lower doses over long periods of time, that can increase your cancer risk. So if you're working around radioactive materials a lot, you're likely to have an increased risk of getting cancer. It just kind of goes with the territory. Chemists also tend to have increased cancer risk, just because we're around stuff that has more carcinogenic effects. Radiation can damage your DNA, which normally kills affected cells, but can sometimes cause them to grow abnormally and become cancerous. There's not like a clear threshold for it. There's also a possibility of genetic defects. I don't have any pictures of that because you can observe them in lab animals, and I'm sure that you could find pictures of people related to that online. The way that we measure radiation exposure is by the number of decay events that a person's exposed to. Two of them are the unit Curie, which is a certain number of decay events per second, and the Roentgen, which is an amount of charge per kilogram of air. They're just difficult to think about units. Human radiation is often reported in REM, Roentgen equivalent man. There's like 3 different classes of units for radiation. One's like the amount that's emitted, one's the amount that's absorbed, and then I think there's a third one that I don't remember what it is off the top of my head. And this is a breakdown of what radiation you might have been exposed to in your lifetime. On average, each of us is exposed to approximately 1/3 of a REM of radiation per year with a bunch of different sources. Primarily, they're from natural sources. If you're going in for a lot of CT scans or like PET scans, then that would obviously increase your radiation quite a bit, but even those are not going to get you into the threshold where you're going to have long-term effects. So remember, it was about 1/3 of a REM per year. Not a number that you necessarily need to know, but just to calm your fears about radiation if you have any. The first measurable effects, which is a decreased white blood cell count, suppressed immune system, occur with instantaneous exposures of approximately 5 to 10 rem. So the amount that you would typically experience in a whole year, multiply that by 30 times, 15 times, and that's sort of like the amount that you would have to get at once to get any noticeable amount of health effects. So it's unlikely that you're going to run into that on accident. Radioactivity is also useful in medicine. For example, in isotope scanning, you can inject things like Tech-99, and Tech-99 will show up in bone scans. So you can like look at where all the bones are in the spooky, scary skeleton of a person. You can also do things like introduce radioactive iodine into the body, and the thyroid naturally takes up iodine in your body, so that can show how well your body is taking up iodine. Or if you have thyroid cancer and you have cancerous thyroid cells that might be all over your body, they take your thyroid out, inject you with a high dose of radioactive iodine, and then all the thyroid cells that might be throughout your body pick up that radioactive iodine, which kills them, and then you're clear, hopefully, of thyroid cancer. You can also tack them onto antibodies, and then those can go target different areas in your body and figure out where those things are going. You can also use radiation for killing things like cancer, since it's great for killing cells. And so they can put you under a big machine or inside of a machine that basically just has well-directed rays of radiation that like circle around you, so it hits you from a bunch of different sides, all targeting one part within you, and then everything that's along that path also gets a little bit of radiation, but it's kind of focused on that one point. Anyway, that's all the stuff that I've got for radiation, radioactivity in the slides. Any questions? Some other fun stuff with radioactivity. The like really old glow-in-the-dark watch faces and clocks and stuff, sometimes that's got radioactivity in it. So if it glows in the dark without you having to charge it up with light, that's radioactivity. And if you want to learn more about that, look up the Radium Girls.